Okay, this is section 9.1, and 9.1 is called basic combinatorics. What combinatorics means is the number of combinations or ways something can happen. Okay, so we've got three distinct events, and how many ways can they be arranged? We're going to call the events A, B, and C. I'm going to draw a tree diagram. First event, A, is either A, B, or C. If A happens first, then B or C has to happen second. Looking down this first branch down the tree, A, B, and then C is last, or A, C, and B is last. If B happens first, A or C has to happen next, and then vice versa. Oops. So if B, A, then I'm looking at ending with C, or B, C, I'm ending with A. If C happens first, I'm going A or B. And then C, A, B, C, B, A. This is 6 different ways. Okay. So this one I can call A, B, C. This one A, C, B. This is the order they're happening in. B, A, C, B, C, A, C, A, B, C, B, A. 6 ways. This is often called, this is a tree diagram, what I drew out here. Sometimes this method of just calculate everything up is called the brute force method. Okay, there is a shortcut method. I can look at it as this. How many different options can I choose first? 3. I can choose A, B, or C. After I've chosen A, B, or C, I have 2 choices left because I've used one of them up. And the last one is just 1. It also equals 6. There are 6 ways this can occur. The principle that I can multiply ways that they occur together is known as the multiplication counting principle. And that's where I write out the blanks and I write the ways it can occur. Sometimes it's the same for all of them. Sometimes it's reducing by 1. Sometimes it's radically different. So, using it, because sometimes this brute force method is way too big. So, the Tennessee license plate here consists of 3 letters. This is example 2. Just a second. So this is example 2. The Tennessee license plate starts with 3 letters and then 3 numbers. And it looks like the example they give is CSK 605. The question is, how many license plates could we have? Well, there are 26 letters in the alphabet, and we can use all 26 of them. Okay? And yes, you could have a license plate that's AAA. That's legal. There's no restriction on that. No letter or digit can be repeated. Oh, I missed that. There is a restriction on this. So my first one has 26 letters. My second one, oh, there is no, okay. Part A is if there's no restrictions. Meaning I could theoretically use all 10 digits here too. I could have 0, 0, 0. So I multiply those all together and I get 17,500 nope, 576,000 different license plates I can make. Part B says if no digits can be repeated or letters, means I have 26 letters for the first one, 25 for the second one, 24. So there is no AAA license. My first digit is 10, 9, and 8. And again, I'm just multiplying this. 26 times 25 times 24 times 10 times 9 times 8 equals 11,232,000 ways. Still a lot of ways, but not nearly as many. Some states that's not enough for, and they have gone to 7 or are using 5 letters just to get more ways. So again, this is the number of ways something can happen. This matters because we need to know how many license plates or how many cars we can have registered in a state. I'm sure California is more than even that top number. So something to note. This notation means n factorial. Factorials grow very quickly. So let's say I'm doing 6 factorial. A factorial means I'm multiplying it by everything, counting down. I don't really need the times 1, but that gets really big. 120, 360, 720. 6 factorial. I didn't want to go to 10 factorial. It's going to take a while. So a permutation of an n set is n factorial. So can you determine the number of 9-letter words you can write from these? This is example 3, and the word is dragonfly. Now, because I've got no distinguishable letters, I can put them in any order. There's 9 for the first one, 8 for the second, 7 for the third, etc. That's 9 factorial, which is, told you these grow fast, 362,880 different ways to arrange those 9 letters in the word dragonfly. In butterfly, here I have 2 T's. Okay? Meaning I can't tell. I can put those 2 T's in 2 different spots and not be able to tell the difference. What I do here is I divide that by 2 factorial, which is just 2. So it cuts it in half. 2 factorial is 2 because it's 2 times 1. Now if I get to a one with more repeated words, bumblebee, I have 3 B's and 3 E's. So I'm going to divide by 3 factorial for the B's times 3 factorial for the E's, because I won't be able to distinguish those. And I've still got a lot of ways that a lot of different arrangements of letters that would make things that mostly aren't words, but distinguishable arrangements of letters, 10,080. That's still a lot. Okay? So permutations are of n objects taken R at a time. So let's say I want permutations. I want to pick 4 people from a group of 10 and assign them rank order of 1, 2, 3, 4. One of the keys to permutations is order matters. And there's this notation for permutations, NPR. And we'll let our calculator do a lot of this. But the basic formula for this is n factorial, like where we were, over parentheses n minus r factorial. Okay? R has to be some number between 0 and n. You can't choose 11 positions out of a group of 10. That doesn't make any sense. So we're going to do the first couple without a calculator, and then I'll do some with a calculator. So this is example 4. 6, 4. This is part A. 6 factorial over 6 minus 4 factorial. I calculated 6 factorial just a little bit ago. 6 minus 4 is 2. 2 factorial is 2. This is 360. Part B, 11p3. That's 11 factorial over 11 minus 3 factorial. That's 11 times the bottom is going to be 8 factorial. 10 times 10 times 9 times 8 factorial. And I'm just stopping at 8 factorial because I've got an 8 factorial on the bottom and stuff can cancel. So now I've got 11 times 10 times 9, which is 990. Now we're going to do this in more general terms. NP3. That is n. So the bottom is going to be n minus 3 factorial. So the top is n times n minus 1 times n minus 2 times n minus 3 factorial. And that's n. We'll leave it in factored form. N minus 1, n minus 2. Okay. So applying permutations. We'll probably use the calculator for this. So 16 actors answer a casting call to tryouts for the role as dwarfs in a production of Snow White and the Seven Dwarfs. How many different ways can the director choose the 7 roles? There's 7 dwarfs, that's 16 P7. Because they can assign them to different dwarves, a different person as a different dwarf is a different way that they can be assigned. So now I'm going to show you how to do this on the calculator. Okay. So I press the math button. I scroll over to PRB, prob, for probability. So math, scroll over to prob, NPR, and 16, enter that, 7, enter. 57,657,600 different ways. That's a lot of different casts. Okay. So again, here I've said order matters. What we're going to do next is called combinations, where order does not matter. Okay. Permutations, order matters. Combinations, order does not matter. Okay, combinations. If you notice next to the NPR was an NCR. This is often called N choose R. And the formula is pretty similar to permutations, except we also divide by R factorial instead of just N minus R. So permutations was this. So you can see the similarity. There's also there's an abbreviation for this called N choose R, which is written with these parentheses. NR, there cannot be a fraction bar between them. It's just N over R. Again, same thing. R has to be between 0 and N. Could be 0. Okay, so we're going to talk about example 6. And we're going to decide permutation or combination for different scenarios. So a president, a vice president, and a secretary are chosen from 25-member garden club. That would be a permutation because I'm choosing 3 and president and vice president are different roles. That'd be 25p3. Again, I would be using a calculator for that. A cook chooses 5 potatoes from a bag of 12 potatoes to make potato salad. Does the order that he picks the potatoes matter in? No, he's cutting them all up and mixing them together. So that's 12C5. That's how you're normally going to write it. But you'll see this in the binomial theorem, which we did some binomial expansions, and we'll be doing that in the next couple days. We did binomial expansions last year in Algebra 2. And we actually used some of these. You let your calculator do all that calculation for you. A teacher makes a seating chart of 22 students in a classroom of 30 desks. Choosing 30 of his desks for 22 students, and the order absolutely matters. So this is a permutation. That's going to be a very, very large number. Here, this is how big this number is. Keep in mind that trillion is 10 to the 12th. That's more than a trillion trillions. That's bigger than the mass of the Earth in kilograms. Okay. So, that's example 6, picking between the two. Example 7 says, in the Miss America pageant, 51 contestants are to be narrowed down to 10 finalists who will compete on national television. And how many possible ways can the 10 finalists be selected? Again, the order, there isn't a set order going into the finals. You're just picked as a finalist. So order does not matter. So this is a combination, 51C10. And let's do that on the calculator. Math. Scroll over to PRB. This time it's just NCR instead of NPR. Factorial is also there. And there's some random number generators in here too. If you ever use those, it's probably going to be using random integer most of the time. 51, choose 10. That's a lot. That's 12 billion. Almost 13 billion if I round up. Ways to choose my 10 finalists. Okay. So that's some examples with combinations. Let's talk about another one. Georgia Lotto requires winners to pick 6 integers between 1 and 46. The order in which you select them does not matter. The lottery tickets are always printed with the numbers in ascending order. How many different lottery tickets are possible? So this is example 8. Order does not matter, it said. That means combination. There's 46 numbers. You're choosing 6. 46, choose 6. That's equal to 9,366,819 different tickets. There's probably one winning combination among those. Hint, probably not worth playing the lottery. Doesn't often pay off. There's too many possibilities. And yeah. Okay, selecting pizza toppings. Armando's Pizzeria patrons, any combination offers patrons, okay, Armando's Pizzeria offers patrons any combination of 10 different toppings: pepperoni, mushroom, sausage, onion, green pepper, bacon, prosciutto, black olives, green olives, and anchovies. How many different ways can pizza be ordered? If we choose 3 toppings. So if we choose 3 toppings, does the order matter for the toppings? No, doesn't matter if you choose mushroom, sausage, and green pepper, or green pepper, sausage, mushroom. Those are all the same. This is a combination. Well, this is example 9A. This is a combination. We had 10 toppings, you get to choose 3. And that is equal to 120. That's a manageable amount of different pizzas. When we think about it, let me make that 10 a little neater. B says we choose any number of toppings. Well, this is where it gets to be a pain. 10 choose 10 is 1. Now I could choose 9 of my 10. 8 of my 10. Okay, and that gets to be kind of a pain. There's an easier way to think of this. You can there are 10 toppings. You either choose yes or no for each topping. I don't know how many blanks I put down yet. Ten choose 10 was 1. You either choose yes or no, so there's 2 options for each topping. That got very messy very quickly. Or that's 2 times 2 times 2, aka 2 to the 10th. There's 1,024 different ways I could order this pizza. Okay? And if we're counting yes, no subsets, they're often 2 to the n is the formula. So that is a common thing, or there's 3 options, 3 to the n. If repeats are a thing, it's often to the power of n for how many we have instead of NPR or something like that. So, analyzing an advertised claim, example 10. A national hamburger chain used to advertise that it fixed its hamburgers in 256 ways since patrons could order whatever toppings they wanted. How many toppings must be available? Well, they said 256 ways. That means 2 to the n, either yes or no on every topping out of 256. So to solve this, I can convert to logarithmic form. Log base 2 of 256 equals n, and that is 8. They must have at least 8 toppings to satisfy the claim that they have 256 different ways you can order your hamburger. That is section 9.1, basic combinatorics.